So, yeah, we'll have our usual class session tomorrow. All right, so let's pick up from where we were to some degree. So, we're talking about atomic response to near resonant driving, where we have a resonance between two energy levels. It has some Bohr frequency associated with that energy difference. And we're driving it with some a dipole allowed transition with some monochromatic field that is oscillating at some laser frequency or light frequency, omega sub L. Okay? And one of the things we were looking at last time was how big of a dipole moment is induced when we drive the system. In a similar way that we study this classically, when we look at material response and we induce dipole moments in the matter, and those dipoles will radiate. Okay? So that's one of the things we can think about. How does the quantum mechanical description of that differ, or is it the same as the classical? So quantum mechanically, we can solve for the induced dipole moment. Yeah?
Just make sure I'm following. The dipole moment operator is just the regular expression for the dipole, but with x replaced by the operator x or something like that?
Yeah, so the dipole moment is always the mean position of the positive charge relative to the negative charge times that charge, right? As we have classically. If we think about this as, we have a nucleus and we have some electron, then this R is the position of the electron. Classically, we would, if we put for this charge distribution, say, which has, say, some net charge E, this would be minus E R. That would be the classical dipole moment. Quantumly, it's this. So it's the position of the electron relative to the core, the nucleus, but at the end of the day, when we're thinking about it, restricted to the subspace of the two-level system, it takes a very simplified form, which is this one, okay? And this is in the rotating frame, okay? So that's the dipole operator restricted to the two-level system where we only have these off-diagonal elements because the mean dipole moment of either the ground state or the excited state is 0, okay? So we have basically raising the dipole operator is associated with absorption and emission. It is raising from the ground state to the excited state or lowering from the excited state to the ground state. Okay. And so we can use the Schrodinger equation, or more generally the master equation, to solve for the induced dipole moment as a function of time. And we're looking at it as the average, the expected value of that operator, and that's given by the trace of the operator with the density matrix. And because the dipole operator has this form, it looks like it depends on the coherences, the superposition that is related to the superposition between the ground and excited state. And it's the real part of this times e to the minus I omega t. You have a question?
Yeah, sorry, just to double check. That says induced dipole momentum.
Yeah, it should be moment, whatever. What I see and what I write is not the same thing. I don't know what goes on in this brain, but that's just my
Yeah.
Right, yes.
I was thinking for a second.
Yeah. Okay, so we did that last time. I flubbed here and there with the signs, but now this is correct. It was correct in the notes, but this is the induced dipole that depends on how much coherence are we inducing. We couldn't imagine we start in the ground state, and in steady state, we will induce some superposition, right? And that superposition or that coherence is driven according to this equation. These are the optical block equations or the master equation. They include both the driving and the detuning and spontaneous emission, and this is what we find, okay? And it has this form of this complex Lorentzian prefactor times what we call the population inversion. How much population is in the ground state relative to the excited state, okay? And in particular, when we have weak driving, and what it means to be weak, remember the Rabi frequency is the energy associated with the interaction between the dipole and the electric field. So that's the definition of the Rabi frequency, okay? Depends on the strength of the electric field, which is the working with square root of the intensity, and the dipole matrix element, okay? And when the driving is weak, which is to say the intensity is sufficiently low, such that this Rabi frequency is small compared to that, then as we'll double check again, if we started in the ground state, then most of the population is in the ground state, and a tiny amount is in the excited state. The correction terms are of order omega squared over this stuff. Okay? Yeah.
The L subscripts are for laser, not
Hey,
LiMAR, right?
That's correct.
Okay.
L subscripts for laser or light. Okay, so the electric field of the laser. And when that's true, then we can plug this in using this definition, assuming everything is in the same direction, then the coherence here that's induced, the induced dipole moment, is proportional, this coherence is linearly proportional to the strength of the electric field. And that proportionality constant is called the polarizability. It's a complex number, it has a real and imaginary part. The real part is related to dispersion, and the imaginary part is associated with absorption, okay? It's the same thing that we saw in classical electrodynamics, okay? So, at least in this limit, when we have weak driving, when this is true, and most of the population in the ground state, this looks exact, this is the Lorentz oscillator. In steady state, the dipole oscillates at the frequency of the drive, and it looks like the charge on a spring with a certain resonance frequency, and it looks exactly the same. Yes, Dom?
So you're saying dispersion, absorption, stuff like that. So if we have a bunch of these quantum systems, a whole bunch of stuff, when we shoot a laser at them, we see all the fancy dispersion stuff we saw in class.
Yeah, so I can imagine I have a gas of cesium atoms, and he has them in the lab he works in. And if we were to shine a laser beam through that, what's going to happen to that light? Some of it's going to get absorbed. It'll then be re-emitted. We call that scattering of the electromagnetic waves. Some of it will be forward scattered into the same direction as the beam and will interfere with the beam and will cause an index of refraction. So as we studied, some of you studied with me last semester, we saw this, everything that's true that we thought of the Lorentz oscillator matter exactly follows when we think about this not as a charge on a spring, but as the binding that we get from quantum mechanics. In this order, it's like a harmonic oscillator when the driving is weak. Okay. In addition, what we saw is that. Okay, I'm missing those notes, but I know what I'm talking about here. So we also saw that this equation, the equation, well, not this one, which is the equation for how the population in the two levels, the probability to be in the ground state or the probability to be in the excited state, how it changes. This is the master equation. The master equation tells us that the way populations change depends on something about the coherences. In fact, it depends on the imaginary part, the V part of the block vector. That's why absorption is related to the imaginary part, right? V was the imaginary part. Remember, rho EG or rho GE was U plus IV over 2 or something. Anyway, the point here is that we have this equation that says something about, oh, there's coherences and superposition that changes the population. But often we think about this in, like your sophomore physics as, oh, there's, we have energy levels and, things jump. You can have absorption, or you could have spontaneous emission, or you could have stimulated emission. And that's a kind of population rate equation picture that looks quite different than the Schrödinger equation, because it's an equation for probabilities. It's not an equation for probability amplitudes. But those equations have under the hood the Schrödinger equation, and we can find them in the limit that the coherences go to steady state. So after a few spontaneous emission times, after the transients die down, which is a few nanoseconds, if we're, let's say, in the first excited state of an atom, it's a typical lifetime, then we can substitute in for the steady state solution that we found over here and get equations of motion for the populations. And they are as expected. The excited state decays through a combination of spontaneous emission and stimulated emission, and it grows due to absorption, okay? And this is minus the rate of change of the population in the ground state, assuming that we have no other levels that things leak to, so that everything is conserved. And when we solve this, so we're assuming at all times the total population is conserved. Okay? So with that, we can solve these equations in steady state, and we found that the population in the excited state in steady state was equal to something we called S over 2 plus 1, and the ground state is 1 minus that, which is 1 plus S over 2, 1 plus S, where S is defined to be the Rabi frequency squared over 2 divided by delta squared plus gamma squared over 4, which we call the saturation parameter. It's called the saturation parameter because it tells us how much we saturated this transition. Let's say how we started with some population in the ground state, how much did we saturate the possible population inversion, okay? What's important here is when S is much, much less than 1, then the number in the excited state is S over 2, approximately, and the number in the ground state, this is all in steady state, is 1 minus S over 2, to lowest order in S, if we do a Taylor series expansion. S is proportional to omega squared. So to lowest order to first order in omega, this is approximately 0 to order omega over delta, blah, blah, blah. And this is 1, which was the weak driving condition that I had. So when I'm weakly driving, I guess I'll put in the details here. So that's what was set up there, okay? So that's where we get this from. So to first order in omega, we have a linear response. But the atom is not a harmonic oscillator. The electron is not in a harmonic potential. It's in the 1 over r potential. It's very anharmonic when it starts stretching it. And the optical response to driving, even in 2-level atom, is nonlinear optics. It's not linear optics because we don't get the driving that is generally linearly proportional to the amplitude. We have a nonlinear response. It's what we call a saturable absorber, okay? Because if I were to look at, I can see that the population in the excited state has to first order something proportional to the intensity. So really, if I were to put that into this expression over here, I'd have something that was a constant plus something that's proportional to the intensity. Which is to say that the optical response of a gas of atoms to light will have an index of refraction that's proportional to the intensity. That's called the Kerr effect, okay? So at 2-level, an atom is really a nonlinear, unless I drive it very weakly, then it looks like a linear optical response. That's for my linear optics friends in the audience. Yes, Don?
Try and relate this to other stuff where we have distortions like this, nonlinearities, and would the population be the analog to a signal and you start seeing harmonics?
Yeah, I mean, so if you take a course in nonlinear optics, the atomic response gives you various harmonics, multiple harmonics. It's a little bit, in a 2-level system, you can't get higher harmonic generation, you really just get more of a Kerr effect. You don't get harmonics, but it's the same thing. We'll talk maybe a little, we will talk about that next semester. Okay, so, very good. All right, so, oh, by the way, the stimulated emission rate equals the absorption rate, which is, and what comes out of the solution when we plug in for the steady state coherences is that's equal to omega squared over 4 divided by delta squared plus gamma squared over 4 times gamma, which you can get from Fermi's golden rule, where the density of states is associated with the fact that this has a finite, it's not it's not a sharp line, it has a finite line width that's broadened due to spontaneous emission, okay? But this, if we look at this expression, this is equal to S over 2 times gamma, all right? Which is the population in the excited state, in steady state, times gamma when I have weak driving, okay? So I can think about, the idea is that I have absorption equal to the emission, and that's this rate is sometimes called, often, I always call it gamma sub S is equal to this. It's another name for it, which we call the photon scattering rate. I mentioned scattering a moment ago. So let me go back to this picture over here. I'll come back and bring that up in a moment. So, you know, I'm sending in laser light, and there's some absorption and some emission. And some of that emitted light goes off in some random direction, okay? According to the probability, if the direction that goes into, this is determined by the dipole radiation pattern that some of us studied together when we studied in Jackson, you know, how much power goes into a particular solid angle. So the random direction, a photon comes in, a photon goes out. So the absorption rate has to equal the emission rate in steady state, because in a two-level atom, there's no vibration, there's no heat. There's no other place for that energy to go. Once the energy goes in, the energy must come out. In a solid or in a molecule, some of that can go into vibration or phonons or rotations, but if you have a two-level atom, it's not exactly true. Some of it can go into the recoil, but this is called the recoil shift. It's not a big amount of energy. But there's photon scattering here. We're going to talk about photon scattering a little bit later in the semester when we think about the nature of the non-classical light. In some sense, we think about this, might think about this as spontaneous emission, right? And a photon is emitted into a direction into which there was no photon. But that's not exactly the right picture. We'll think about that. Because I ask you this question: if I'm detuned from resonance and I'm in this weak driving regime, if I'm detuned, as to say the difference between my laser frequency and the resonance frequency is not zero, what is the frequency of this scattered photon? How many of you think that it's the frequency of the Bohr energy? And what do you or is it the frequency of the laser? What's your thought? The laser. Why? Energy is conserved. That's an excellent thought as well. In addition, we see here that the dipole is oscillating at the frequency of the laser. It's radiating at that frequency. Okay. Now, it's a little bit more complicated when I drive the system very hard, because some of the energy is in the interaction. It's not just, and so I can excite the energy such that I get fluorescence in addition at the resonance frequency. That's called resonance fluorescence. Okay? Yeah.
So when we do like baby quantum mechanics and they first introduce us to this stuff, they'll
Yeah.
say, oh, your atom absorbs a photon and emits a photon, and
Yeah.
that's what all is happening.
Yeah.
And the angular momentum laws respect that picture.
Yeah.
But it feels weird to say that we're absorbing a photon when we're driving it between populations, like part way, like.
Well, no, I mean, it's really interesting points here. The light, we're going to have to think about this in terms, right now, we've thought about this only in terms of a classical field, so there ain't no photons. So we'd have to really solve the problem carefully, as you suggest. I need to think about a quantum version of this where there are photons. Okay? Now, as we're going to see, classical light has an certain number of photons, what we call classical light. It's not classical because it's got photons, but the quantum state of light that's closest, that describes the laser, which is called the coherent state, has an uncertain number of photons. So the way in which the different possibility, maybe there was a photon, maybe there wasn't. And the coherence that's in that is essential to driving the coherence in this Rabi oscillation. Otherwise, we don't have Rabi oscillations. So we have to have an uncertain number of photons, and we'll have to think about all the different processes.
So is that's putting that on our
When we'll put hats on that. That may come before fall break or may come after. Yeah.
So earlier you asked like, oh, what is the energy of the light that emitted? And Tristan said, oh, it's related to the laser, right?
Yeah.
To conserve energy. It's not entirely clear. What energy is it? Why does that need to be the case in order to conserve energy? Why can't they?
Well, if the photon had energy h bar omega in, and the photon out had some energy, could the energy go? So there's energy in the incident photon. There's energy in the scattered photon.
I see. So if we're thinking about it one photon at a time.
That's right.
Then yeah.
But it's a little bit more subtle because some of the energy could be stored in the atom, and it could be different, but not in this weak driving regime because everything's in the ground state in the end. Okay, so then it can't have absorbed any of the energy. It couldn't have shifted it in any way. But when you have strong driving, it's a different story. When you have weak driving, you should think about it. That's called elastic scattering. Elastic scattering is to say all the energy in is equal to the energy out. But you can have inelastic scattering in a two-level atom when you have strong driving. All right, excellent. All right, so with that said, yeah.
So if you actually wanted to kick the atom up to the XIC, you'd have to have inelastic. So
And the inelastic scattering will happen when the driving is sufficiently strong that we go beyond this approximation, right? When we start saturating the transition. And as I didn't emphasize, but we talked about last time, in the limit that S goes to infinity, I have equal amounts, okay? I have a half of the population here and a half of the population there in the limit that S goes to infinity, which is to say when this is huge compared to this, okay? So now, in that case, when the population in the excited state equals the population in the ground state, what is how much coherence do I have? 0. The mean dipole moment is 0, which means it's all inelastic. It's all, as we will see, due to the quantum fluctuations, it's really spontaneous emission. There's a difference between elastic scattering and spontaneous emission. Elastic scattering is really about inducing a dipole that coherently radiates versus the quantum jumps. Spontaneous emission is different from inelastic scattering. Even though you might think this is a spontaneously emitted photon because it went out in a direction where there was no photon, it's really not spontaneous emission, it's coherent radiation. All right, lots to discuss, but we got to move on. I would love to have more. We'll have to have the time when we can just chat about all kinds of stuff. Okay, so we've been talking about the two-level atom, where we can learn a lot. But sometimes you might have more than one level or 2 levels. We could have a 3-level atom. Okay. What are some situations where we consider 3-level atoms? Well, we might have a situation, for example, where we have, say, 2 levels that are metastable. They're not connected by a dipole transition anymore because otherwise it would decay. Let me just look at it. I just call this. Let's see. That's really matter. So I'll call this level 1, level 2, and then I'll call this level 3, where there's not a electric dipole allowed transition between these two. These might be, say, two different S states, or one might be an S state and one might be a D state, okay? They could be two magnetic sublevels in a degenerate subspace between the ground state. And this is some excited state. And I want to drive population from here to here, I can do it in a two-level transition, which in a way that I might detune from this, maybe I'll draw this for the moment like this, where I have some laser with some frequency and some Rabi frequency and another laser. So I have two colors such that the difference between the beat note between these two lasers is equal to the Bohr frequency between that. Yeah.
So you're saying via the selection rules, you can never make a transition from 1 to 2, but you can transition from 1 to 3 and from 2 to 3?
That's correct. So this might be two different S states and this a P state, right? Then I can, this is what's called a two-photon resonance. It's on two-photon resonance when the beat note, the difference between these two frequencies is equal to this. This might be a microwave frequency. And these are two optical frequencies. And with an electro-optic modulator, I can modulate one frequency rather than the other at a microwave and drive this system. Maybe there is an actual I could have put on a microwave to do that, but this is another way to do that. Yeah.
Is this a quadruple transition or is this different?
It's not a quadrupole transition. I mean, if it was an S to D, that would be a quadrupole transition.
Okay.
Okay, but I'm assuming here that these are two dipole allowed, so the Rabi frequency associated with either laser 1 or laser 2 is equal to the dipole matrix element between level J and the electric field associated with that laser, okay? They're typically one laser and you just, modulate one to give it a slightly different, or it could be two colors. It could be completely two different colors, okay? This configuration of levels is known as the lambda configuration. And for historic reasons, this is also known as a Raman transition. Raman saw spontaneous scattering absorbing one color and emitting another in molecules, but it's really, calling this a Raman transition is just leftover. Yeah.
So why big lambda? Because big lambda, from a molecular perspective, I think that is the absolute value of MSL. So what is that?
The term lambda is just because this looks like
that's
three-quarter
it?
lambda.
Oh,
That's the only thing. It has nothing to do with anything else.
Okay, all right.
And I could have the other way around. I could have two excited states that are metastable, and I want to draw transitions between these two with some detuning between this guy. It's called this level 1, this level 2, this level 3. You know what this is called? Yeah, this is called the V configuration. We're almost never deal with that.
Actually, that's not 3 levels.
And there's yet another situation where, say, I have a ground state, I have an intermediate state, and a higher excited state. So I have one, let's say 3, 2, I'll call it this way, where, so here's omega laser 1, here's omega laser 2, they have two different Rabi frequencies. For example, this might be a an S state, say, I'll take the case of cesium that I know, where the ground state is actually a 6S state. And I want to go up to a very highly populated state. And that energy might be a UV photon, and I don't got no UV laser around, but I got some optical lasers around that might add up to them. So I can have a 2-photon resonance. Maybe this is the 60S state, okay? Sometimes known as a Rydberg state, a Rydberg state. And I go through some intermediate P state. Maybe I go through the 7P state, because the 6P state has too short of a lifetime. And that's a 2-photon transition. This is a 2-photon resonance with a level that I'm detuned from in this way, okay? These are things are done all the time to manipulate the coherence between two levels where I can't necessarily get there directly, and then go there through an intermediate level, okay? I might do it like this in a Raman transition. This is called the ladder configuration. Okay? Now, of particular interest in these kinds of systems is a situation where I drive the system in such a way that I get very little population in these intermediate levels, and that I can restrict my population in some way that if I start in, say, level 1, I can effectively treat this as an effective 2-level system. I'll get your question in a moment. As an effective 2-level system in some way, even though I need the 3rd level there's no way I can go directly from 1 to 2, but I want to drive the system such that at the end of the day, I can effectively eliminate the 3rd level and treat it as our friend, the 2-level system, once again, okay? That's kind of the most interesting case for us. It's not the only thing we're gonna study. We're gonna see other cases where we drive it on resonance with the 3rd level. There's all kinds of interesting physics there as well. But I want to focus on that. Okay, Donald, you had a question.
Yeah, our energy levels go 1, 3.
I just decided that because I want to call level 1 and 2
Okay.
the levels that I'm gonna ultimately, I can label them any way I like. But if I'm thinking at the end of the day, I'm gonna somehow try to eliminate level 3 and restrict ourselves to levels 1 and 2, then I label them the thing that I'm detuned from, okay, in that way. So, how should I think about the system? So, when the detuning, and typically these states have a finite lifetime, right? I mean, this guy can spontaneously emit, maybe into 1, maybe into 2, right? It's same thing here, this thing can spontaneously emit. I want to be sufficiently far detuned such that I get high coherence and I get very little spontaneous emission, okay? So that means, so when this is much, much bigger than the Rabi frequency over 2, the saturation parameter is small. Okay, so that means that there's little population in 3. When I'm sufficiently far detuned, or even when I'm on resonance, as long as my Rabi frequency is small. Remember, I should have said this here. We come back to the saturation parameter. Let's just look at it when delta is 0. What if I'm right on resonance? Well, in that case, this is equal to twice the Rabi frequency squared over the spontaneous emission rate squared. Okay? So I can have low saturation exactly on resonance as long as my Rabi frequency is very small compared to the spontaneous emission rate. Okay? In fact, remember, the Rabi frequency is proportional to the electric field. So the Rabi frequency squared is proportional to the intensity of the laser. So this is equal to the intensity over some characteristic intensity, because this is a dimensionless quantity, that's called the saturation intensity. It's the intensity of the laser that if I was on resonance, the saturation parameter is 1. This is a property of the atom. Just to get some numbers, so what this says is that when the intensity of the laser equals the saturation parameter, when I equals I sat, the Rabi frequency is equal to the square root of 2 times gamma. Is that right? Gamma over square root. When this is, yeah. Right? So, I happen to know this because I worked in the lab at cesium. The saturation parameter for the first excited cesium is about a milliwatt per centimeter squared. So if I had a milliwatt and I put it in a spot size that was centimeter squared, then my Rabi frequency would be about equal to gamma. And gamma is about, over 2 pi is about a megahertz. So just to give you, anybody who cares about numbers, how big is the Rabi frequency? If you have a milliwatt per centimeter squared on a very strong transition, you get about a megahertz Rabi frequency. Just what the heck, you should know some numbers. Okay. All right, but let's come back over here. So, so when that's true, we will be able to, what we can look at this, what we can say is that we can adiabatically eliminate level 3. What do I mean by that? Well, there's different scales in the problem. There's the detuning, there's the spontaneous emission rate, there's the Rabi frequency. The rate of change, as we'll see when we go through this in detail, the rate of change of the amplitude, the probability amplitude in low intermediate level will be dominated by the detuning and the Rabi frequency. That tells me something about the timescale over which that changes. Whereas if I start here, the timescale over which this changes will be due to the Rabi frequency. So there are fast variables and there are slow variables. The probability amplitude in 3 will try to move very fast, but it's going to be slaved. It can't go anywhere because 1 and 2 are changing so slowly. And the fast variables get slaved to the slow variables. This kind of adiabatic elimination was first done by Oppenheimer with Born in the so-called Born-Oppenheimer approximation, thinking about the motion of nuclei in molecules. The electrons are buzzing around, but the nuclei are like just very heavy. They can't move, and they can't go anywhere. So they're slave to the motion of the electrons. And you can adiabatically eliminate the fast variables and just get equations for the slow variables. We'll see how that works in specific case right now. but that's the essence of what's going on. Okay? Yeah.
So if I want an explicit definition for adiabatically here, it's just anything characterized by this slow being slaved,
Yeah.
being slaved
Yeah,
to slow.
adiabatic in this case just means that at every time what it does depends on what 3 does depends just on the state of 1 and 2. It doesn't have an independent. It follows it in time.
Mhm.
But yes, I would say that in my definition here, we should be more precise. Is this one fast variable being enslaved to the slow? So let's first look at this kind of adiabatic elimination in an easier case where we look at some important physics. Let's go back to the far detuned 2-level atom. Okay, yeah.
So thermodynamics, adiabatic would be like no heat transfer.
Yeah, but it's also about how slow, no heat transfer is a consequence of how you're changing, say, the piston in such a way that you're maintaining the equation of state at all times. Let me continue this, okay? So let's just see how this goes. Let's say I have my 2-level atom and I'm detuned by some amount. This thing has some spontaneous emission rate and there's some Rabi frequency associated with it. And I can look at this problem in the following way. If I'm going to be far detuned, as we said, and far detuned means this, okay? So when we say far detuned, it's really relative to the Rabi frequency. The detuning is huge compared to the Rabi frequency. Then, to the degree to which I can say there's very little population in the excited state and steady state, as we just studied, there'll be the amount of which I'll get lost and be refed is small. We can describe that then by the effective Hamiltonian, okay? The effective Hamiltonian is equal to the Hamiltonian minus I h bar gamma over 2. This is the imaginary part of the excited state has a finite lifetime, and so we add, this is my non-Hermitian Hamiltonian, okay? And in the rotating frame and all of the rest, what we then get is, let's take this energy to be 0, the energy of the ground state, we'll just call it 0, as is my right, and the excited state then is, the energy of the excited state is given by h bar omega times the Bohr frequency, okay? So when we go into the rotating frame, we get minus h bar delta minus I h bar gamma over 2 times the excited state, and then I have the d dot e interaction in the rotating frame gives me this, where I take the phase of the laser to be 0, as is my choice, okay? So that's my 2-level atom, including an imaginary part in the excited state. And so we can then ask, what is the Schrodinger equation associated with the time evolution of this, okay? So, of course, this is a non-Hermitian Hamiltonian, so population won't be exactly conserved, and we'll come back to that in a moment. So from that, if I say, this thing has a ground state and an excited state, I can find the time evolution of the amplitudes, and I get that the ground state in this case is coupled to the excited state. The excited state, I have I minus gamma over 2 minus I gamma over 2. So that's the Schrodinger equation written in terms of the probability amplitudes. We have a coupling between the ground state and the excited state at the Rabi frequency, and then we have this overall phase factor and a decay, let's see, an overall phase factor and a decay of the excited amplitude, okay? Again, this is huge compared to this, okay? And because of that, this thing effectively comes to steady state way faster than this changes. So I can adiabatically eliminate by just setting the time derivative of this to 0 and said, oh, it's so fast, this gets to steady state. I'm going to eliminate this excited state. And I get that this thing, as a function of time, is slave to the slow variable. So I've eliminated this and said whatever this is, it just is adiabatically following what that is. Okay? Because this is huge. And when I have differential equations like that, that's how they solve. When they have very disparate coefficients. Go back and look at Wikipedia about solutions to differential equations for your much better source for that. So with that said, I can plug that back in over here, and I get in this, once I've adiabatically eliminated the excited state, I get minus I minus a gamma squared over 2 minus over I delta minus gamma over 2 CG. Okay? See if I did that right. Get my notes here. Damn you, minus signs. Curses. Let's see. Because there should be a gamma squared over 4. Oh, I know what I did wrong. When you take this to the other side of the equation, it becomes a plus. Yay! So that's a plus, and that's a 4. All right, that's correct. I recognize that. Okay, and this, once I normalize the denominator, I'm going to multiply top and bottom by the complex conjugate, I get the following. Minus I, something I'm going to call delta E LS for the ground state over H bar, minus the scattering rate over 2 times that, where gamma S is as before, S over 2 times lambda, and delta light shift of the ground state is S over 2 times H bar delta, where S, as before, is defined as this. Remember, this is the scattering rate, also known as the absorption rate. Where for two-level atom, what is absorbed is scattered. But what do we see in this solution? What we see is that once we've done this adiabatic elimination, the population in the ground state is going away at that rate. The amplitude goes away at the rate gamma over 2, but there's an additional phase shift relative to what it was without the interaction So the amplitude in the ground state now decays. Why? Because light is being absorbed. So this is the rate at which population goes out of the ground state. But there's an extra phase. And that phase, this thing, is the light shift on the ground state. What do I mean by that?
Difference between the two energy levels?
It's the way in which the energy of the ground state is shifted because it is being perturbed by the light. This is in the absence of the light, in the atom laser, this was the energy level of the atom. But when you put an interaction on the atom, that's no longer the energy eigenstate. The energy eigenstate is changed. And we can solve that, and maybe you did, I hope you did your third problem extra credit, some of you, maybe. You can still do it. You should. By perturbation theory. The perturbation theory is this is my H0, and this is my H int. And to the degree to which this is small compared to that, we know how to do perturbation theory. And perturbation theory tells us how energy levels shift. The light shift is also known as the AC Stark shift. Why is it called the AC Stark shift? Does anyone know what the Stark shift is?
Just like if you apply an electric field to that.
Right. I
The
hope
AC Stark
Professor
shift
Gold
is
taught you
dynamic,
about
right?
the Stark shift. The Stark shift is the shift of an energy level in the presence of an electric field, typically a static electric field. But here,
Field's dynamic.
we're applying an AC, meaning an oscillating electric field. And that causes a energy level shift that we call the AC Stark shift, which is also known as the light shift. Yes?
I think you may have already answered my question based on what you just said about treating it perturbatively, but when you said we're assuming it's adiabatic and we must assume that the nucleus is essentially stationary, that means I have to be considerate of the strength of my fields, right?
Yeah, I mean, there's various levels of approximations and assumptions that we're making. The notion about adiabatic here is not about the Born-Oppenheimer approximation. It's not about how the nucleus is moving. At this moment, we're just keeping the nucleus fixed in space. Okay? The adiabatic elimination here was coming from this. These differential equations have very different timescales. To the degree to which this is tiny compared to the strength of this means that I can eliminate this equation by just setting this derivative to 0 and saying that this guy is just slave to this. It locally follows it. That's what we mean by adiabatic here. Has nothing to do with the nucleus, has nothing to do with Born-Oppenheimer. It just has to do with this separation of timescales.
What I'm getting at is it independent of the strength of the field. Like if I crank up the field very strongly, I go to a very high intensity.
Yeah. Well, if I cranked up the field too much, I wouldn't be able to adiabatically eliminate because then I would not satisfy that.
Yes. Okay. All right.
So we're assuming the field is sufficiently weak that the Rabi frequency is small compared to the detuning.
Thank you.
Excellent. All right. So, where was I? Oh, yeah. The AC Stark shift. So let's talk about the AC Stark shift. And for that purpose, I'm going to go back to my Hamiltonian. Okay? Let's go back to this Hamiltonian and let's look at the eigenstates of the total Hamiltonian. This Hamiltonian, remember H0 was the Hamiltonian of the atom, which was E. These were the bare eigenstates and eigenvalues of the Hamiltonian, okay? That's my H0, and if I go to the rotating frame, I get that this is I subtract off h bar times the frequency of the laser. That's when we remember when we went to the rotating frame, this is the Hamiltonian, the bare Hamiltonian. Okay? Which is equal to minus h bar omega L minus omega Eg. We always, in my class, define the detuning as the laser frequency minus the Bohr frequency. Okay, so it's blue if it's above, and it's red if it's below, and it's positive if it's above, it's negative below. Okay, so this is, and we're going to take the energy of the ground state to be 0. So the bare Hamiltonian in the rotating frame is this, okay? The energy of the ground state we've taken to be 0. So in the absence of the light, in the rotating frame, as a function of the detuning, because the eigenvalues depend on omega L, I can plot the energy as a function of detuning, okay? The ground state is 0 energy at all detunings. But the excited state is minus the detuning. So this is the ground state over here, over here. This is the excited state. This is the excited state. Okay? So those are the energy levels of the atom in the rotating frame as a function of detuning. Okay? Now we're going to perturb them by adding in the dipole interaction. So my interaction Hamiltonian in this is h bar omega over 2 times Eg plus Ge. By the way, if I think about, as we always do, in a pseudo-spin notation, the ground state is spin up. I mean, the excited state is spin up and the ground state is spin down along Z. We always choose that. Then how do I write this Hamiltonian in terms of the Pauli's? Sigma plus, sigma minus. Yes, please.
1/2 identity plus sigma z.
Beautiful, thank you. Excellent. The projector is that. Okay? And the interaction Hamiltonian, the atom laser Hamiltonian in the rotating frame is this. And how do I write this in terms of the Pauli's? Sigma x, sigma y, sigma z. What is it?
X. Just sigma.
This is just sigma x, right? Because this is sigma plus, and this is sigma minus, and sigma plus sigma minus is sigma x. Okay. So we could do, let me just ask you a quick question. To first order, what is the shift in the energy levels? How would you calculate the first order energy level shift according to perturbation theory? What is the shift in the ground state to first order? How would I find it if this is the bare Hamilton zeroth element and this is the interaction option, assuming this is small compared to this? Yep, and what is it? Zero. Same thing is true for the excited state. So the first non-vanishing shift is going to be second order. It's going to be on the order of omega squared over delta squared.
So you're talking about bare Hamiltonian without adding the atom laser interaction?
Yeah.
Bare Hamiltonian has the laser's frequency.
Yeah, that's just because we've gone to the rotating frame.
Okay, so that's just saying if we're just spinning,
Yeah,
well, in the magnetic spectroscopy version, if
That's
we're
right.
spinning at that,
that's right.
that's Hamiltonian.
We always look at it in the rotating frame when we have this kind of
Okay.
time dependence, yeah. Okay, but, so we can do perturbation theory, and if you did the problem set where you would have done it, but let's solve it exactly. Okay, because we can, we don't need no stinking perturbation theory, we could just analyze the whole thing. Okay, so, let's do it.
Crap, this is what I did in the homework, not for
So, my Hamiltonian, the Hermitian part, is equal to minus h bar over 2 times delta times the identity, minus h bar delta over 2 sigma z, plus h bar omega Rabi frequency sigma x. That's the Hamiltonian written in terms of Pauli matrices, okay? Which I can write as minus h bar delta over 2 times the identity plus h bar over 2 times a vector, which I called omega effective, dotted into the vector of Pauli operators, where omega effective has an x component, which is the Rabi frequency, and a z component, which is minus dv2. Some of us have seen this before. So, I ask you now, how do you find the eigenvalues and eigenvectors of this Hamiltonian? How would you do it?
expressing the basis.
The secular equation.
You would write down, maybe you'd write down a matrix, and then you write down the secular equation, and then you find the roots, and the, no! It's not how you do it. No, it's not how you do it. Not for a two-level system, you should never ever do that again in your life, yes?
You can use the magnitude of the Pauli.
Yeah, exactly. So this thing, so aside, if I have a vector dotted into the vector of Pauli's, this is equal to so the vector has a magnitude and a direction. The magnitude of the vector is the magnitude of this vector, which is that. And the direction of this thing is this over its magnitude. Okay? So, given I've written this operator as some number times a Pauli matrix in some direction, what are the eigenvalues of this operator? Yes.
Walk states in that direction.
No, what are the eigenvalues first?
Values, oh, and 2 plus and minus.
It's a map. So the eigenvalues are plus and minus the magnitude of this.
Is there a 1/2?
No. There's a 1/2 over here, but the Pauli's have eigenvalues plus or minus 1. Okay? So this operator has this eigenvalues. Okay? Because whether it's sigma x, sigma y, sigma z, sigma in any direction in space, their eigenvalues are plus or minus 1.
I think some mathematicians define the qualities differently.
Well, screw them. And so the thing with the plus eigenvalue, that comes to your answer, Tristan, what is that state? The state that has eigenvalue plus here.
The block vector associated with that direction.
Right, it's spin up. The block vector is a little different. The block vector is a vector in space. This is a vector in Hilbert space. So it's spin up along that direction. And minus is spin down along that direction. Where that direction is the direction of this vector. Okay? So if I think, and now I come to your, here's the sphere, the unit sphere. Okay? It has a z-axis and a y-axis. Let's, for simplicity, because it's just always hard to draw this, let's say that I have red detuning, so that the detuning is negative, so that I would have my omega effective pointing like this, okay? It has, this is the z-axis. It has an angle theta relative to the z-axis, where its x component is omega, and its z component is minus delta. Okay, I made it positive because then I could have theta less than 90 degrees, otherwise I have to think about trigonometry and I don't want to. Okay? So, what is theta? Trigonometry says that the tangent of theta is equal to omega over minus delta. Opposite over adjacent, right? So, theta is the arctangent of that. That's the direction in which this vector is pointing. It has no phi component because there's no y component. So, given spin up, this is the direction E sub n on the unit sphere. So that's the block vector. It's the direction of that thing. And now I'm asked you, how do I express these states as superpositions of the ground and excited state, or equivalently, superpositions of pseudo spin up and pseudo spin down?
Cosine theta over 2.
Beautiful. Times the ground state, which is excited state, that's spin up along z, plus sine theta over 2, the ground.
No phi?
Nope, that's what we got. And this guy was sine theta over 2 e minus cosine theta over 2 g. Okay? So the eigenvalues of the Hamiltonian, e plus or minus, are equal to minus plus or minus h bar over 2 omega squared plus delta squared. Okay? We just diagonalized the Hamiltonian, meaning these are the states, the eigenstates of the system, including the bare binding of the electron to the nucleus and the interaction with the laser field. The states that we get, these states are known as dress states. They're called dressed because the electron is dressed by the photon. And the states without the laser on are called the bare states. Okay? And if we were to draw with the energy, this is really the equation for a hyperbola. So if I were to draw, what I would find is that the energy levels have this avoided crossing structure. So the dotted lines were the bare energy eigenvalues. The solid lines are the shifted levels. And what we see here, if I'm red detuned, oh, did I get lucky? Just happened to randomly choose the colors. If I'm red detuned, what I see is that the ground state is shifted down slightly. And if I'm blue detuned, the ground state is pushed up a little bit, okay? If I'm right on resonance, the dress states are what? When delta is 0, what is theta? Well, tangent theta of infinity, pi over 2.
Yeah, it's 5 over 2.
And so, in that case, my plus state and minus state are excited plus or minus ground. I have equal superposition of the two. But when I'm far off resonance, when delta is much, much bigger in magnitude than omega, then tan theta is approximately theta, means theta is approximately that, okay? And in that case, the dress states are one, if I looked at what the dress state that is connected to the ground state, what I see is that the dress state, the dress ground state is the ground state minus delta over 2 gamma, because it's the omega over 2. So cosine is approximately 1 and sine is approximately theta over 2. This is the perturbed ground state. The perturbed ground state has a little bit of excited state superposed in. We call that an admixture because somebody didn't know what a mixed state was when they used that word. It's really a superposition. But I've admixed in some excited state when I did this perturbation, which means that the perturbed ground state has a dipole moment. And that induced dipole moment interacts with the field. That's called the light shift. Okay? And so we get both the fact that the dress states have admixture of the two levels within them, and the fact that the energy levels are shifted a little bit. They can be shifted a lot if I'm closer to resonance, but if I'm far off resonance, as is the case that we have, and in that case, when I'm far off resonance, if I look at this solution over here, where is it? Here it is. This is the energy that's shifted in the ground state. If I look at this, the lowest order is equal to h bar times omega squared over 4 delta, which is equal to h bar s delta over 2, which is what I said over there. So the light shift on the ground state when I'm far detuned falls off like 1 over the delta and goes like the intensity. Okay? The scattering rate, which is the rate at which we had absorption over here. So this thing is proportional to omega squared over delta. This thing is this when I'm far detuned goes like omega squared over delta squared. Okay, so this part of it is proportional to omega squared over delta squared. So if I'm sufficiently far off resonance, if my detuning is very big compared to the Rabi frequency, I can get a huge light shift with almost no absorption, which is how an optical tweezer works. You can trap an atom by going way far off resonance, and you'll get a huge potential to trap the atom and almost no absorption, because the absorption falls off like the square of the detuning, but the light shift falls off like 1 power thereof. And if you, well, you'll see in your next homework. Now we're about a half a lecture behind, but we'll discuss more about this in the problem session, so we better abandon ship. I'll take other questions outside.
I was off by 1 negative somewhere.
Yeah, well, it's been fun.
Very familiar.